Okay, today we're going to talk about cryptography. The first thing we're going to look at is something called the substitution cipher. A substitution cipher replaces each letter in a message with a different letter, following some established mapping. Simple example of substitution cipher is called the Caesar cipher, or sometimes called a shift cipher. Essentially what we do is we move the alphabet so many letters for each letter. So let's look at an example of a simple Caesar cipher with a shift of 3. The message we want to encrypt is we ride at noon. So there's several ways we can do this, but the method that I typically use is I start out with the alphabet. And I didn't leave enough room. Let's try this again. We're off to a good start today. Okay, so we have our alphabet, and then we're going to shift 3 letters. So instead of starting with A, we start with D. And somehow I'm off a letter. Huh. Okay, so I found my error. So now we're encrypting the message, we ride at noon. So first letter is W right here. So I change that to a Z. The next letter is an E. That gets changed to an H. Next letter is an R. That gets changed to a U. The next letter is an I. That gets changed to an L. Then we have a D, which is changed to a G. And we have another E, which is changed to an H. Then we have an A, which is a D. We have a T, which is now W. We have an N, which is now Q. We have an O, which is R, and another O, which is R, and then another N, which is Q. And that's it. So now we're going to decrypt this message if it's encrypted using a shift cipher with shift 5. So again, the same method here. Maybe I can get the alphabet right this time. And now we want to shift 5. So if we move 5, we're going to start with F. And that time we got it right. So now we have an encrypted message we want to decrypt. So we're going to be looking at the second row here. So we're going to find G here. And it's a B. Then we're going to find Z. And it's a U. Then we're looking for D. And that's a Y. And we're looking for K. K. Make sure you stay on the bottom here, which is F. Then we're looking for N, which is I. And we're looking for another K, which is F again. We have Y, which is T. Then we have D, which is Y again. Then we have X, which is S. Then we have M, which is H. Then we have F, which is A. Then we have W, which is R. Then we have J, which is E. Then we have X, which is S again. And then we have A, which is V. Not sure why that's there. 550 shares. Unless they just wanted to make it in groupings of 3, so they added a nonsense letter, which we'll be doing in a later method. Okay, another example of this. Same principle. Decrypt the message if it's encrypted with a shift cipher with a shift of 9. In other words, mapping A to J. And we write our alphabet out. Okay, now we're going to start with J. And we got it right. So now again, we're decrypting, so we're going to look at the bottom. Okay, our first letter is B. Nope, wrong place. See, I made that mistake. You gotta be careful. Make sure you decrypt from the bottom, encrypt from the top. So that's an S. Then we have an N, which is an E. Then we have a W, which is an N. Then we have an M, which is a D. Then we have a V, which is an M. Then we have an X, which is an O. Then we have a W. Oops, I did it again. Which is an N again, right here, W. Then we have an N, which is an E again. And then we have an H, which is all the way down here, which is a Y. Send money. Okay, now we talk about encryption security. The security of this method, well, it depends on the encryption key being difficult to discover, and in this case, it's not really that difficult. This is an example of how many different ways a 4-letter word could work, and you could change it to the different things, and how with the right kind of machinery you could figure out the encryption. The next thing we talk about is what's called a brute force attack. It's a method of breaking encryption by trying all possible encryption keys. Because if we know this is done, With a shift cipher, we can just keep doing different shift ciphers over and over again. So then we have something that's called substitution mapping, where we just randomly map the letters of the alphabet, and in this case the numbers, with random letters till we get them all filled out. This would be more difficult to calculate or to do by brute force, but again, not necessarily impossible. But let's look at this and see what we have. We want to encrypt the message March 12th, 0300. So we need to find our M here, which is a 6. Then our A, which is a 2. Then our R, which is an S. Then our C, which is a Q. Then our H, which is a T. Then we have 1, which is Z. 2, which is N. 0, which is Y. 3, which is I, and then 2 more zeros. And that would be the encryption. Okay, now we want to do it the other way. We want to decrypt the message. And let's look. Our first letter is C, so we go across the bottom and we try to find C here. That's P. Then we're looking for 2. That's it down here. That's A. Then we're looking for S. That's here. And that's an R. Then we're looking for V, which is here, and that's a T. Then we're looking for X, which is here, and that's a Y. Then we're looking for 2 again, which is an A. Looking for V again, which is a T, and then we're looking for P. And P is right there, 9. So again, this would be very difficult to do, but it can be done, which is what we're going to talk about next. Not to mention it's difficult to encrypt and decrypt. So unfortunately, like I said, certain letters in the English language are used more often than others. Using something called frequency analysis. Other languages have the same issue. Certain letters occur more often. So it wouldn't be easy, but it would be possible to use the knowledge that certain letters occur more often and which letters occur most often to decipher the code, even when it's mixed up like that last one. So then we come up with something called a transposition code. Cipher. A transposition cipher is one in which the order of characters is changed to obscure the message. So we have something. We have meet at First and Pine at midnight. And we want to use of 8 characters long. So this is how this works. Essentially, you take and you write out the message. Meet at First and you put in nonsense. I'm just going to put in X's here. And then you would write it this way. MRNESETEXEANXEDXFPXIIX. Okay, now we have the same thing here. Decrypt this message using the method above and a table with rows of 5 characters. So let's see, do we have what we need here? 3, 6, 9, 12, 15. We have 20. So we're going 4 deep. C, E, E, I, A, I, M, N, L, N, O, G, L, T, R, V, And I missed one. No, I didn't. H, N, W. So then we go across, and this is what? Call me in the morning, and then we have nonsense letters. So that's how that works. Okay, now that's still not too difficult to figure out. So another method that is used is we have a code word to tell us the order of the columns. So a more complex version of this rows and columns based transposition cipher can be created by specifying an order in which the columns should be recorded. To make the encryption key easier to remember, a keyword would be used. For example, the keyword was money. It would specify that rows should be 5 characters each, 5 letters of money. The order of the letters in the alphabet would dictate which order to read the columns in. So since E is the 4th letter in the word, the earliest letter in the alphabet from the word money, the 4th column would be first, followed by the 1st column, the 3rd column, the 2nd column, and the 5th. So what we would do is write out our word, our message, in 5 letters, so 5 rows. Buy some milk and eggs. And again, just nonsense letters. So now, using our money, we said the 4th column should be first. So we would rewrite our message like this. The 4th column first. Then we would go to the 1st column. Then we would go to the 3rd column. Then we would go to the 2nd column. And then we would go to the last column. And that would be our encrypted message. And now we're going to do another one like that. The keyword is help, so we're going 4 letters across. And again, our nonsense X's. They don't have to be X's. They can be different letters. A lot of times you use ABC or XYZ or something of that nature. So now we're doing help. So E is the lowest or the earliest letter in the alphabet, so it would be the 1st column. E is 2nd, so this is the 1st one. Okay, then we go with the 1st column. Then we go with the 3rd column. And then we go to the 4th column. And that's it. Okay, now this one's going to get more difficult. So we're looking at our cipher, and we've got the word prize for our code. So the way to look at this is to set up something like this. So we got 6 by 4 letters. Now what this is saying, the D is saying that the last column should be the 1st place. So we take these first 4 letters and they go in the last column. Okay, next would be the 5th. So that's the next 4 letters. E-N-U-S. Okay, then it's the third one, I, third. So we go R-E-D-E. And then 4, first column for the P. So we're R-I-K-A. That puts us here. And then the 5th thing is the second column. Or the second column is the 5th thing. We have T-S. Oops. Where did I mess up? I did the wrong section here. This is supposed to be there. This is supposed to be here. A-I-E-R. And then this is I-K-A-T. These 4 right here. This is where the R-E-D-E was supposed to go. It can be difficult to get straight. And this would be the last one. S-O-Q-R. I will tell you, I think there might be one like that on the homework, but there definitely isn't one like this on the exam. So our message becomes airstrike on headquarters, and then a nonsense V. Okay, the next shift method we use is, well, first of all have been susceptible to frequency analysis since each letter is always mapped to the same encrypted character. The more advanced methods get around this weakness. Encrypt the message "See me." Use a basic Caesar cipher with shift 3 as the initial shift, but shift a substitution one place after each character. So we're going to start off with a simple Caesar cipher with shift 3. And let's do our shift of 3. And this starts with E. And I don't think I guess 5 letters shouldn't be too rough. So, we start with our first letter, which is S here. So our first letter is V. Okay, now we need to shift this over 1. So now we have D. And what am I looking for? E. so on here, which gives me an I. Okay, so now we'll shift to the next. It starts with F. And so on. And there's the E again, and that gives me a J. Okay, we need to shift it again. G, H, I, J, K. And that brings us to M here, which is S. Shift again, and we start with H. And there's E there. So L. And one more time. I. And there it is, and we get M. So that's our message. Now that's a really tedious one. Okay. So let's go the other way. See what we come up with. We start with an initial substitution shift of 3. So our first letter is K. That's H. Our second letter is I. L, M, N. Oh, wait, here's I. So that's E. Now remember, we're going up to the top row. Our next letter is Q. And that's an O. Oh, that should be a P. No, that should be it. Third row, Q. L, M, N, O, P, Q. That's an L. There it is. Be careful. You have to go to the top row. I didn't go to the top row initially. Okay, then we have R. Which is R is L again. And then we have V here, M. And that is O. And the message is hello. Okay, again, that method is time consuming as well. Okay, the last thing we're going to talk about is something called modulus arithmetic. Modulus is another name for the remainder after division. Remember the good old days when you learned how to do long division? Before you learned decimals and you just put remainder 4, remainder 3. Well, that's what we're looking at. We're looking at the remainder. So something, for example, if you had 17 mod 5, it would be equal to 2. If you divide 17 by 5, we get 3 with a remainder of 2. So 10 mod 3 would be 3 into 10, which is 3, remainder of 1. So the answer to A is 1. Okay, 15 mod 5 would be 5 goes to 15 times the remainder of 0. So B would simply be 0. That's mod 5. Well, let's do later here. 2 to the 7th is 128. And 5 goes, well, 5 goes into 12 twice. 10, that leaves 2. Bring down the 8. 5 goes into 28. 5, 25. Our remainder is 3, and that would be the answer to C. So let's do a couple more of these. 7 goes into 23. 3 times 21 with 0. Not 0, 2. B here we have 15 7 goes into 15 twice. 14 with a remainder of 1. And C, 2034. Okay, that's 2, which is 14. 6, bring down to 3, that's 9. 63, bring down to 4. And we have 0, so our remainder is 4. That's all it is. Now, some of these numbers get a little large. So, to calculate A mod n on a standard calculator, divide A by n. So we're simply going to say en 3, 1, 3, 4, 5, divided by 419. So 3, 1, 4, 5, divided by 419, and I get 4.8090691. Now subtract the whole number part. So subtract 74. And we get 0.0890691. And then simply multiply that by n, which in this case is 419. And I get 339. Now, on some of these where you're using your calculator, you may find that it's something like after you do the multiplication, you'll get something like maybe 338.992977599 or something like this where it's real close. That's because of a rounding error in your calculator. Just round it up to the whole number. That would be the correct way. So the next thing we're looking at is using the exponential rule. So it says if we have a to the b power mod n, it's the same as saying a times or a mod n to the b power mod n. So let's look at what we got here. We got 12 to the 5th mod c. So in this case, a is 12, b is 5, and n is 7. Okay? So essentially, we can rewrite this as 12 mod 7 to the 5th. So 7 goes into 12, well, once, with 5 remainders. So 12 mod 7, well, that's 5 to the 5th. Which is, where's my calculator? 5 to the 5th equals 3,125. Okay, then we have something called the exponential or modular exponential power rule. It says a to the b mod n to the c is mod n is equivalent to a to the b times c mod n, which is also equivalent to a to the c times mod n to the b mod n. And it says to show that these are equivalent. So let's start out. And what do we know? Well, our a is equal to 3, our b is equal to 4, and our c is equal to 5, and n is equal to 7. Okay, so we want, for the first part, we want to find what 3 to the 4th mod 7 to the 5th mod 7. What is that? Well, 3 to the 4th is 81. 81 mod 7 to the 5th mod 7. Okay, 81 mod 7 turns out to be 4 to the 5th mod 7. This is 1024 mod 7, which gives us 2. Okay, Our second one, we can rewrite this as 3 to the 4 times 5 power mod 7. So this is simply 3 to the 20th power mod 7, 3 to the 20th power. I did it the hard way. I guess we could have used the previous rule. 3, 4, 8, 6, 7, 8, 4, 4, 0, 1 mod 7. And that comes out to be. And the last one, we have 3 to the 5th mod 7 to the 4th mod 7. So this is 243 mod 7 to the 4th mod 7. This is 5 to the 4th mod 7. This is 625 mod 7, which also comes out to be 2. Okay, so now this is go back to the previous thing and find what 10,000 mod 7 is. I say, let's do it both ways. So we have 7 into 10,000. That's 1, which is 7, 3, bring down my 0. That's 4, which is 28, 2, bring down my 0. That's 2, which is 14, 6, bring down my last 0. 8, which is 56. So my answer is 4 going that way. Now going back to that formula, we had a to the b mod n is equal to a mod n to the b mod n. So we had a to the b. A is 10. So I have 10 mod 7 to the b, which is 4, and all that mod 7. So 10 mod 7, well, 7 goes into 10 once, 3. So this is 3 to the 4th mod 7. Okay, again, we could do this using the formula, but I did the math. This is 81 mod 7, and this does turn out to be 4. I believe we calculated it earlier. All right. Where was it? I swore we did that earlier. Maybe not. Yeah, there it is. Nope, that's not it. But it comes out to be 4. Okay, this last part about public key cryptography, if you're into computers, that tells you a little bit about how encrypt your computers. They use modulus for that. It's the last section in the chapter. If you're interested in it, you can read it. You won't be tested on it, so we won't be covering it. I don't feel it's as important for you guys to deal with that. So that's all for this chapter. You guys have a good day.